So we're about ready to wrap up our study of polynomials for now. And in order to do that, we're going to draw another parallel with the integers. So this definition at the top is our replacement for the definition of a prime integer. So call a polynomial irreducible if whenever you for that polynomial f as polynomial g times polynomial h, you have to have the degree one of the two factors to be 0. So if you think about our definition of a prime integer, it was the only way to factor it was with like 1 times itself. So p was a prime, meant the only factors were 1 and p. So here this is something similar, but what we're saying is that that either g or h is a constant, not a polynomial, but a constant polynomial. So for example, plus 1 is irreducible, even though we can figure out something, like we can write x plus 1 is 2 times a half plus a half. So this doesn't count as a true factorization. This is a trivial factor. So x plus 1 is irreducible because the only way to factor it is trivially like that. Notes on this. So first, irreducibility depends a lot on what field you're using. Irreducibility. So this depends on f. And so, for example, we can take things that are irreducible in some settings and not in others. So like x squared plus 1 is irreducible over r, but not over c. So if we consider our field of constants to be r, then we can't reduce x squared plus 1. But if we consider our field of constants to be all complex numbers, then I can factor this as x plus I times x minus I. I is that square root of negative 1, so I squared is 1. All right, as another quick example, so x squared minus 7 is irreducible over q, but not over r. Because over r, if I'm allowed to use real numbers as my constants, then I can factor this as x minus root 7 times x root 7. All right, one more note of irreducible polynomials. Irreducibles act like primes. In the integers. Okay, so we will factor polynomials into irreducibles the way we factored integers into primes. And that leads us to our next set of definitions and theorems. So unique factorization in F says every non-constant polynomial in F factors into a product of irreducible polynomials, and they're unique up to order and multiplying by constants, those trivial factorizations we consider. All right, so this theorem, this unique factorization in F, is really similar to the theorem of arithmetic, which said the same thing about integers. It said every integer can be factored into a product of primes that are unique up to order. All right, and then we have a fundamental theorem of algebra. This is different than what's above. So what's above is similar to the fundamental theorem of arithmetic, but the fundamental theorem of algebra takes it even a step further. It says that if you allow your field of scalars to be C, if you allow all coefficients to be complex numbers, then every non-constant polynomial has a root in the complex numbers. And so what that means is I can take any polynomial in Cx and factor it completely by pulling out all those linear terms for every single root. So I can factor it completely into a product of linear terms over C. Now, in order to state the corollary that you might with, we need to talk about what the multiplicity of a root is, and that is something you might already know. So the multiplicity of a root, A is said to have multiplicity k if x minus a to the k divides f, but x minus a to the k plus 1 does not. So let's look at an example of that. So let's take a polynomial. I'm going to already have it factored. So x minus 2 to the 4th times x minus 3 squared times 4 has the roots 2 and 3 and 4, but 2 is a root of multiplicity 4. 3 is a root of multiplicity 2, and 4 is a root of multiplicity 1 in that polynomial. And then our corollary to this fundamental theorem, so the fundamental algebra said I could factor completely into a product of linear terms. And then from there, what we can say is that the number of roots in C, counting multiplicities, is actually just equal to the degree of f. And so we see that in this example. If you expanded that all out, if you expanded the x minus 2 to the 4th and x minus 3 squared and x minus 4 and multiplied them all together, you would get a 4, 5, 6, 7th degree polynomial. And if you count those roots and the multiplicities, 4 and 2 and 1, 7 roots counting multiplicities. So that's our corollary to the fundamental theorem of algebra. That if you allow factoring over the complex numbers, then the number of roots counting multiplicities is actually just equal to the degree. So one thing that this means is we can take, so for example, if f of x is an nth degree polynomial, and ourselves to use any complex numbers as coefficients and as roots, then we know we can write f of x as there might be some constant we can pull out, and then we're just going to get all the roots to various multiplicities. So a1 is a root of multiplicity k1. 2 is a root of multiplicity k2, and we keep doing that all the way up until maybe the mth root of multiplicity km. Then we know by this fundamental theorem is that k1 plus k2 plus dot 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 all the way up to km is equal to the degree of f, so n. So we can take f, we can factor it completely down to these linear terms. We might have to put that constant c in front depending on what the leading coefficient was. But otherwise, the sum of those roots, the number of those roots counting multiplicity, will be the degree of the polynomial.